Now that we know what a composition is, we can talk about inverse functions. All right, inverse functions are functions that undo each other. All right, so let's go back to my little example of my new store that I'm going to open, my new shop, Simply Lattes. All right, my coffee shop here. So I'm going to get some merchandise here, okay? And I want to mark everything up 50% of what I buy it for. So I'm going to buy it, I'm going to mark it up. So, in other words, I got this function here. My merchandise price is going to be 1.5 times X, which is how much the wholesale price, all right? What I bought it for. So then I decide, you know what? I'm gonna boost my sales. I want to have a sale, and I'm gonna make it 2/3 of the original price. All right. So everything is 1/3 off or 33% off. We could say. In other words, the new price for my sale is 2/3 of what the regular sale price is. All right. So let's think about this. Maybe I have. A beanie cap, maybe, okay, or a hat for $4. I usually sell for, I buy it for $4. That's the wholesale price. Well, if I bought that hat for $4, what am I usually going to sell it for? Well, my M of X, M of 4 is going to be 1.5 times 4, which is $6. Okay, so I'm selling it for $6. Well, on my sale price is going to be take 6 and drop it into my sale price function, and it's going to be 2/3 of 6, and 2/3 of 6 is, well, that's 12 divided by 3. Oh, that's 4. Okay, interesting. Now, maybe I buy a shirt or sweatshirt, okay, for $12, and I'm going to print it and sell it. All right. Everyone's going to want to buy my T-shirts for my Simply Latte shirts here, right, or sweatshirts, whatever they are. All right, so that's going to be 1.5 times 12, and 1.5 of 12, that's going to be $18. All right, my sweatshirts cost $18, but today on sale, my sale is going to be 2/3. I'm sorry, not 12. Now, to find the sale price, I'm going to put the 18 in here. I got to figure out what my sale price is, because normally they're $18, but today 2/3 of 18, you can buy them for that's, well, 1/3 of 18 is 6, so 2/3 of 18 is 12. Oh, interesting. All right. Well, one more. Let's see. Maybe we have a coffee cup here. All right. So this is a fancy reusable coffee cup. Okay. I buy them for $7. I'm going to sell them 1.5 times 7, and when 1.5 of 7 is 10.5. Now I got to figure out what to sell it for on my sale today only. All right. And so plug in 10.5 into my sale function, and I'm going to say, well, 2/3 of 10.5. You may have guessed it. Go plug that in a calculator if you want. It's going to be 7. Well, what happened here? Well, you can probably see we started with a price, a wholesale price, and that ended up over here as what the sale price was. All right, and you'll notice that happened every time. If I bought it for $12, marked it up, took the sale off, and I'm right back at 12. Okay, same thing for the 7. Well, what's going on here? You know, we have two functions, but it seems like one is undoing the other. So let's go ahead and compute these here. Let's do a composition. Let's take our sale price and plug M of X into the sale function, all right? So our sale function is 2/3 of X. That's what the sale function is. And now we're going to plug in our merchandise, or our markup function, which is 1.5x. Well, when we do that, 2/3 times 1.5x, 2/3 of 1.5 is 1. x, or just x. That's kind of interesting. So when I put x in and I mark it up and then I make the sale, I end up with x. Or if I reverse that, if I start with the markup function, 1.5 of x, that's my markup function, okay? And then I want to put the sale function inside of that, so I put the 2/3 x inside of that. Well, if I do that, 1.5 times 2/3, well, that means 2/3 plus half of 2/3, okay? And that is going to be 1. If you want to work this out, you could change this 1.5 into a fraction. This is 3/2 times 2/3, which is 6/6, which is 1x, or just x. Okay, so moral of the story here is this. When we compose these functions with each other, we just get x. Compose them either way, we get x. X is what we put in, x is what we get out. Because these are inverse functions. Inverse functions undo each other. They are exact opposites. Okay, they undo. Okay, so we have two functions, f and g, and they are inverses of each other. If and only if, when you put g of x into f, you get x. When you compose f of x into g, you get x. Okay, and that's what we call the inverse function. We say g is the inverse of f, or we can write it this way. G of x is the inverse f. We put a little exponent, -1 up here, of x. And that -1 means the inverse of x. I'm sorry, of f, of x. All right? Okay, so f of -1 means the inverse. So that's the deal. That's an inverse. They undo each other. So the first thing we need to do here is we need to be able to test to see if two functions really are inverses of each other. All right? Then we'll work on finding them. So if we take f and we compose it with g, we're hoping that we get x in the end. All right? So let's take f, which is 2 times something plus 3. Notice I write an empty parentheses there. Okay, now let's put g of x inside of there, x minus 3/2. Now let's do the arithmetic. So we have 2 times x minus 3/2. Well, that is just x minus 3. And then we have the plus 3. But the minus 3 plus 3 cancel, and this is just x. And that's good. That's what we're hoping for. Now, if we have g and we compose it with f, then we get g is this guy right here. So g looks like something minus 3/2. X minus 3/2. X is our input. Well, what are we putting into the input? We're putting f of x. So f of x is 2x plus 3. So we're putting f into g. And we get this. Well, let's simplify. We've got the plus 3 minus 3. So that's going to be 2x on top over 2. And these 2's will cancel. And we get x. And that's what we're going for. So yes, these are inverses of each other, so we can say that g of x is the inverse of f. Okay? Yes, they are inverses. Okay, we can also say that f is the inverse of g also. It goes both ways. All right, maybe try this one out. If you want to pause it and try it out, go for it. We're going to compose them with each other. We're going to take f and compose it with g first. So f is 2 times blank squared. That's a definition of f. And what are we going to put in there? We're going to put g inside of f. G is this thing right here. So we're going to put the square root of x over 2 in there. And when we square that square root, we're going to get 2 times x over 2. 2 times x over 2 is x. That's good news. Now we got to check it the other way. It's got to be true both ways here. So we're going to put f of x inside of g. So g is this square root function. G is defined as a square root of something over 2. And what goes into the something? The something is 2x squared. All right. So the 2's cancel there. We've got the square root of x squared, and the square root of x squared is x. Okay. Now, we actually got to be careful here. Okay. I'm going to take that check off there. Okay. Because remember working with the square root of x squared a while ago? It's actually the absolute value of x. Okay. So this is only true if x is a positive number, all right? So this is necessarily, in general, not an inverse. In general, g of x is not f negative 1 of x. However, if we're just talking positive numbers, then it is, okay? So again, the reason here is because of this square root. Remember, when we take a square root, we get positive numbers. Okay. So that one's not really an inverse. We've got to watch out for that, okay? And so we'll see that x squared does not have an inverse. If we were to say that x was positive there, that would be a different case. All right, one more. F of g of x. We're going to take f, which is 4 times blank minus 8, and we're going to put g into f. Put g into the blank. So we got x over 4 plus 2. If we distribute this out, we get 4 times x over 4 is x. 4 times 2 is 8, plus 8 minus 8 coming from the end there. And that's great. 8 is great. We get x. That's a good sign. That's what we're hoping for. So now g of f of x is going to give us g is blank over 4 plus 2. That's our function. Sum the input over 4 plus 2. We're putting empty blank everywhere there's an x. And we're going to put 4x minus 8 here. Now, I've got to be careful. Remember, when you're dividing here, you got to divide both of these by 4. Break it up into 2 fractions if you want. That's going to give us 4 divided by 4 is going to be 1x. 8 divided by 4 is 2. Plus 2, and that equals x. So they both come out to be x when we compose them both ways. So yes, g of x is the inverse of f. All right. That's the idea there. Make that a little. All right. Okay. Here it was not because they both didn't equal x in the end. All right. And up here, the first one, yes, it was true. It was a function. All right. Or an inverse function. So that's how we check to see if it is an inverse. How do we find an inverse? Well, what happens is when we're doing an inverse, the input becomes the output, and the output becomes the input, okay? So the key here is that the inverse reverses the coordinates of the function. So if we have a set of ordered pairs, x, y, then the f negative 1, or the inverse function here, is going to reverse those and spit out the functions y comma x. Okay, they flip it around. They make the input the inverse, makes the input the output. All right, so x goes in, y comes out. Then the inverse takes y in and spits x out. That's kind of the idea. All right. Here's a nice little picture that might help. If x goes into this machine called f of x, the machine spits out y. Then if you put y into the reversal machine, f inverse, then that's going to spit out what we started with, x. And that's what an inverse does. It reverses what the other function did. So to find an inverse, we're going to first replace f of x with y. So we're talking x's and y's. Swap the x and y's or interchange them. Solve for y. And then if it is a function, then we can write it as f inverse. And we can verify by plugging one in and the other. Okay. All right, so how does that work? Well, we write this as y equals, we want to find the inverse here as the instructions. Y equals x plus 7. Then we're going to swap these two and write it as x equals y plus 7. Now, solve this equation for y. That's the next step. So we swapped them or we interchanged them. Let's solve it for y. So subtract 7, x minus 7 equals y. So our new function is f inverse equals x minus 7. And we can check that out by composing them, which we won't always necessarily do, but f of negative 1 of x is going to be x plus 7. That's what f of x is. And if we put this guy in here, we get x minus 7 plus 7, which is just x. And if we try it the other way, the inverse composed with f, well, the inverse we said was x minus 7. So we've got x minus 7. And if we put the original function in there, we get x. So yes, indeed, this is the inverse, which we can kind of see. Adding 7, subtracting 7, those are opposites. Okay. All right, let's try a couple more. We won't check these necessarily. I'll let you leave that for you to check there to practice that. But let's see how it works. Rewrite it as a y. Reverse the x and the y. Solve it for y. Subtract 6 from both sides. Divide by 2. And we end up with y equals x minus 6 over 2. You can kind of tell by looking, this was multiplying by 2, and then adding 6. Here we're subtracting 6 and dividing by 2. Those are reverses, or inverses. So we should write that f negative 1, or the inverse of f, is x minus 6 over 2. What if we do something like a cubic? Still the same process. Rewrite as a y. Swap the x and the y. Now let's solve this for y. Subtract 1, x minus 1, from both sides, that is. Okay, don't cube your yet. You could, but it's going to get kind of messy if you don't do it right. So we now have y cubed equals x minus 1 over 8. Now don't worry about this side over here. Don't try to clean this up. Just let it build up and get all funky like. Don't try to simplify anything, okay? Now we'll take the cube root of both sides because cube root is the opposite of cubing because we're trying to get y by itself. And we end up with y equals the cube root of x minus 8. Nope, sorry, 1 over 8. That whole thing right there. And that is our inverse function, which we like to write as f negative 1 of the cube root of x minus 1 over 8. All right. So that's how we find an inverse. There's our steps. We replace f of x with y, swap the x and the y, solve for y, and then that's your inverse. So we saw how to check to see if something's an inverse if we had two equations. Now we want to see if something is or has an inverse if we look at the graph. All right? So we saw that we ended up with a function a couple examples ago where we had a function that did not have an inverse. All right? So we need to know that before we go looking for one. All right? So here's the key. For a function to have an inverse, it must be 1 to 1. Meaning a 1-to-1 function must have a different output for every input. Or for every x, there's one y, and for every y, there's one x. Okay? It's identical. Okay? So let's think about this here. The question is, does f of x equals x squared have an inverse function? Well, let's find out, all right? So let's think of the function f of x equals x squared. If you plug in negative 3 into x squared, negative 3 squared is 9, right? Plug in negative 1 squared is 1. 0 squared is 0. 1 squared is 1. 3 squared is 9. So we just plug these into the function f of x, which is x squared. Now, remember we said that f inverse just reverses the coordinates. That's what an inverse does. It takes the output, makes an input, and the input and output. So this becomes 9, negative 3. We just reversed the x and the y coordinates here. If we reverse these coordinates, we get 1 comma negative 1. If we reverse these coordinates, you can't tell because they're both 0. Same thing here. Flip these around, you can't tell. They're both 1. Flip these coordinates around, you get 9, 3. So the inverse takes the output, makes an input, and an input and output. So the question is this a function? Remember, for a function, every input has to have an output. Okay? Well, here it says when 9 goes into this function, we get negative 3. But here it says when 9 goes in, it gets positive 3. Well, this little machine can't make up its mind. Is 9 become negative 3 or does 9 become positive 3? How about when you plug 1 in? When you plug 1 in, you get negative 1. But here, when you plug 1 in, you get positive 1. So this is not a function. Okay, so this inverse is not a function. So there is no inverse function because it's not a function for x squared. If we plot these points, we have 0, 0, 0, 0. We've got 1, negative 1. We had 1, positive 1. And then we had 9, 3, and 9, negative 3, which is off the charts here. Okay, so there's the graph of these guys. Now, remember back when we talked about functions a while ago? We had this thing called the vertical line test. So we could say, well, if you can draw a vertical line and it crosses through 2 points, then this is not a function. So the purple thing here is not a function. Okay, so yes, the thing we started with, this is the graph of y equals x squared. That is a function. Draw a vertical line anywhere, and you'll only touch 1 point. That is a function. But when you try to make an inverse, the new thing is not a function. Now, we didn't have to go through all this. See how this shape is the same? It just kind of falls over, and it actually, this is reflected across a line. And the line is right here, y equals x. This is a reflection across here, okay? If you were to fold, if this was a piece of paper and you were to fold on this line, this parabola would fold right over onto this one, okay? It's the reflection across this line, y equals x. Now, all right, we didn't need to go to all this to tell, all right? All we had to do really was look at this black graph of y equals x squared and draw a horizontal line, because the inverse is going to fall over and that's going to be a vertical line. The vertical line test tells us if something is a function. The horizontal line test now tells us if an inverse function exists, all right? So the horizontal line test will tell us if a function has an inverse, okay? Function f has an inverse if there is no horizontal line that intersects the graph of f at more than one point, okay? In other words, here's a function. It's a line. Does this have an inverse? Well, if we were to draw horizontal lines, will any of those lines cross through more than one point? Nope. So the answer is yes. F negative 1 exists. Okay? The inverse of f exists. Okay? How about this one? Is it possible to draw a horizontal line through more than one point? Easy, right? So no, let me put it down here. No, in this case, the inverse of this function does not exist. So not all functions have inverses. Okay, you can't just come up with an equation that would magically undo all this. How about this one? Well, this one you got to be careful here. These all touch at one point, right? Now, what about this? Well, if you were to zoom in here, and we can only zoom in so far, it looks like it's horizontal, but it's not. And we got to know something about x cubed. When you have x cubed, 0 cubed is 0. But when you go a little bit to the right of 0, you have like 0.1. 0.1 cubed is something bigger than 0. So this point is going to be a little bit above the axis. This one's going to be a little bit above, a little bit above, a little bit above. So this is actually, even though you can't tell, it's actually going up and down. All right, it looks like it's flat, but it's not. So we've got to kind of think about what's going on with the function x cubed. So yes, in this case, f, the inverse of f of x exists. Not finding it at the moment, but we just know it exists. So the horizontal line test tells us if it does or does not exist. And one last thing here, it's equivalent to say, is a function one-to-one. So saying a 1-to-1 function, that is equivalent to saying, does it have an inverse? All right. Or we might say f inverse exists. So here we phrase this question as determine if it has an inverse. We could ask the same question and get the same answers. We say determine if it's one-to-one. Is it one-to-one? All right. Same thing. Checking to see if it's one-to-one means checking to see if it has an inverse. All right. Those tell us the same thing. All right. Well, we're going to leave it at that. And we can look at some graphs maybe in class there, but that's the big idea. All right. We did some compositions, and we found out that when we flip the x and y's, we get inverses. And the special thing about inverses, when you compose them, they undo each other. I hope that helps. Thanks for listening.